This afternoon is Julien Berestycki, who is going to talk about branching processes with competition by pruning of Levy trees.
Okay, so so thank you very much for the invitation. It's a great pleasure to be giving a talk in this wonderful conference. So I'm going to talk about actually. Let's see, does this work? No. So I'm going to talk about maybe two things actually. So the first one is indeed, I'm not sure why it's not. The first thing is population with competition. Okay, thank you. And if I have time, depending at when I finish the first topic, I'm going to talk about something which is very related and which is the question of exceptional times for the number of types in generalized Fleming geoprocesses. So this is again a talk about models of population, and this is very related to some of the things that Alison has presented this morning. And I'm going to start by recalling a few basic facts and things I'm going to need about models of population where I don't have any interactions between individuals. So the model I'm going to consider is what's called a CSBP, a continuous state branching process, which is a Markov process on the set of positive numbers. And because I assume that there is no interaction between individuals, if I start with a population with X individual, X is positive, and Y individuals, and then I just take the sum, then it's the same as if I started one population with X plus Y individuals, right? And this this relation here, which I expressed as a convolution of the laws of the process, characterize completely the law of the CSBPs. Now, this is a very well studied class of processes. There's a very rich literature about them, and their law is characterized by what is called the branching mechanism, which is a function psi, and psi has this form which is written here, and you see that there is a linear term, there is a quadratic term, and then there is this integral against a measure on R plus, which is satisfies some integrability conditions, and it turns out that this guy is the Laplace exponent, must be the Laplace exponent of a spectrally positive Levy process. Okay, and I'm going to make some assumptions about this function psi in this talk. I'm going to assume that my function psi is such that my process is conservative, which means that at all time the process is going to stay finite. There's not going to be a finite time where it can blow up and reach infinity suddenly. I'm also going to assume that my process is critical or subcritical, meaning that the expectation of the size of the population is decreasing or staying constant on average. What happened pathwise to the population in large time is a bit more complicated than for Galton-Watson processes, but I'm also going to assume that not only it's subcritical, but it's kind of subcritical or critical such that in fact I do have extinction in finite time. Okay. So now if I take again this relation, which tells me that if I start with X plus Y, it's the same as taking can decompose a population of size X plus Y in a population of size X plus a population of size Y, it begs the question, okay, so can you construct these processes for all starting size of population simultaneously, right? Is there a way of coupling all those things? And there is actually two approaches to do that. And the first one is you can view it as a generalization of the Ray-Knight theorem, and is essentially due to work of Duquesne and Le Gall and Lejean and Le Gall. And there is another more recent approach which is building also on the work of Bertoin and Le Gall and later Dawson and Lee, which is to use Levy-driven stochastic differential equations. Okay, so I'm going to try to briefly explain the idea of both approaches now. Okay, so the first approach is the following. So what you do is you start with okay, so you start with a process H, which is a process of X, okay, and this process is going to be called the height process. And I'm not going to give a lot of details, but essentially it's going to encode a forest of trees. I'm going to explain a bit more about that in a moment. It's a process which is non-Markovian, and its law is also determined, of course, by psi. And there is a way of constructing this function h, this process h, by using by starting with a Levy process with exponent psi. So, in particular, there is a case which I'm going to come back again and again, is the quadratic case. So if your function psi of lambda is just lambda square over 2, then this function h is just a reflected Brownian motion. Okay? In that case, it turns out it's Markovian, but it's only case. So the thing about this process is that you can make sense of the local times. Okay? So I'm going to call LXT like this. This is going to be the local time when I stop at position x on the x-axis. Okay? I look left of position x at the height t. Then I see a local time that I'm going to call LXT. And the theorem here, which is, as I said, mostly due to Duquesne and Le Gall, is that if I look for each v, I look what I see, so left of TV. So TV, okay, let me maybe go to the next slide. Okay. So TV here, what is TV? Well, it's the first time where I accumulate v units of local time at level 0. Okay. So up to this point, I have a local time at 0, which is v. Okay. And then I'm looking at height t, and in this pink strip here, I'm looking at what is the amount of time that the process h, this white curve, spend in this pink strip, and this I call LTV of t. And the result here is that as a process, for each v fixed, as a process, this has low PV, so this is a CSBP started from initial population size v. Okay, but because you can now vary your TV, you can vary v. This encodes simultaneously all starting population size. Okay, I hope this is okay. Okay, and in fact, you have the whole flow here of the CSVPs, meaning that you could define a process if you want to with two time parameter s and t, and you're going to say that the fraction of the population at time t which descend from an interval of length v at time s, well, you can define it like that. So the only thing you have to do is you're going to look at what happened between height s and height t for this process. And so you can encode the whole flow of the population here, right? So you can, one upshot of this construction, as we will see, is that you can really make sense easily of the notion of genealogy here, because this h function encodes real trees, of course. Okay, so let me say now a few words about Dawson and Lee's SDE approach, okay, which builds on earlier work of Bertrand Le Gall that Alison already mentioned this morning. So, so here the idea is you're going to write this stochastic differential equation, which depend both on the parameter v and t. So you see that here v, yt of v, so y0 of v is always v, of course. So this is v here can be interpreted again as a starting size for the population. If you interpret yt of v as population size at time t, and then you have those terms. So you have this minus alpha integral of ys of v ds. So you can interpret this alpha as a death rate for your population. Then you have a Wright-Fisher noise. So this W here is a Brownian white noise in time and space. And then you have this last term here, which is an integral with respect to a compensated Poisson measure, n tilde, whose intensity is ds times d nu times pi of dr. So if your Poisson measure n, so the uncompensated one, has atoms Si, nu I, and Ri, what this means is that at time Si, you're going to see a jump of size Ri, so R here is the size of the jump, if and only if nu I, which is kind of a mark that you use to filter atoms, to thin down your process, if nu I is less than the size of the population Y Si minus of V. So, so you see here, this makes sense from the modelization point of view. So you have the right. So you have to think of those atoms as events where one individual in your population suddenly gets a very large offspring, which create a positive jump in the size of the whole process. So the rate with which those jumps arrive has to be proportional, of course, with the size of the population. So that's why you get this integral for nu between 0 and ys of v. Okay, this makes it proportional to the size of the population, and of course the measure pi, which is here, this pi of dr, is the same pi which was appearing in the definition of my branching mechanism psi. And the theorem in Dawson-Lee tells you that there is existence and uniqueness and strong uniqueness for the solutions of such equations, and that the solution of this equation is in fact has the same distribution, it's inequality in law, as my local time process, seen like that of my function h earlier. So this is again a flow of CSBP. And here, of course, if you want to define this as a flow with two time parameters, s and t, it's even easier. You just, instead of taking your integrals between 0 and t, you just take your integrals between s and t. Okay? Okay. So that was for population when you don't have any interaction. And what I want to do now is I would like to incorporate some more realistic feature in my population model. In particular, I would like to incorporate some form of competition. So, so here is a very deterministic model for the growth of a population with competition, which is very well known. It's a logistic growth equation. And what it tells you is that you have a population which is growing at rate b, but also there is a form of competition pressure because maybe a resource is limited, or there is a small probability that individuals meet and compete with each other, which gives you a negative drift which is quadratic. Okay, and you can of course study the stochastic version of this equation by adding a Brownian noise to it, and if you do that, you get this Feller diffusion with logistic growth. And you can think of this solution of this equation, of this process, as the scaling limit of a process where you have a Galton-Watson or production with some mean which will correspond to B. You will have a variance in the reproduction mechanism which will correspond to the gamma parameter, which is here, and you have a death rate which is Cn for each individual in the state where your population has size n. Okay, so again you can interpret this as saying as there is a probability C that each pair of individuals meet and then one kills the other at each generation. So if you do this in such a way that you have a non-trivial scaling limit, then what you obtain in the end is going to be the solution of this stochastic differential equation I wrote. Okay. So Amaury-Lambert studied generalization of this kind of processes where you're going to have more general branching mechanism. So the branching mechanism in this equation, which is written here, is essentially the quadratic one, right? This is the psi of q equal q squared over 2. So if you want more general branching mechanism, it's a bit more complicated, And the way that Amaury Lambert was able to do it is by using something called the Lamperti transformation, and he showed that by time-changing Orstein-Uhlenbeck processes, he's able to obtain those generalizations. I'm going to give another way of thinking about them in just now, right? So you can, I'm going now to do exactly what I did for the branching without competitions. I'm going to give you an SDE, okay, which is going to encode those general population size process with competition. So, right. So here you see what's written here is exactly the same equation I had before, except I have this new term here which is added. Okay. So this guy here is exactly what is accounting for the competition, right? And I'm going to ask this capital G to be of a certain type, right? So what I'm saying here is that the population evolves according to the same equation I had before without competition, right? This is just a pure branching. Plus I add the negative drift, okay? Which depend, of course, on the size of the population I'm considering at the time I'm considering it. So what I'm asking is that G is actually the integral of from 0 to z. G of z is integral from 0 to z of small g of t dt, okay? And G is a positive function. So this ensures, for instance, that the drift is more negative when your population is larger, which makes sense if it's a competition term. And the typical example I want to think about is the case which corresponds to the same logistic competition. So I'd like to think about capital G of z is z squared. Okay? And this corresponds to, of course, taking g of x equal a constant time x. So, okay, let me say maybe one or two more words about this equation and what you can read in it. So, when v is fixed, what you have is that the negative drift at time t is, of course, g of zt of v. And what that means is that each individual, so let me think of z between 0 and capital Z of t, zt of v, as one individual in your population, right? My population is an interval of the real line. So each the individual z, I'm going to think about it as being killed at some rate, which is small g of the population it sees to its left, which is, of course, small z, right? So the total rate of killing is indeed the integral of small g of z dz between 0 and capital Z, right? So what's important here is to realize that by writing my equation like that, in some sense I have already encoded in there the notion that there is an order on the individuals, and that individuals are always killed by those to their left. Okay? So by mimicking the techniques and the results of Dawson-Henley, we can show that this stochastic differential equation here has a unique strong solution, okay, which I will call the logistic branching process with branching mechanism C and competition mechanism capital G, which is going to be CAD lag for HV. And the other thing you can see here is that if you start from two different starting population size, let's say U, V, and W, and you look at the difference ZTW minus ZTV, so that's the fraction of the population at time t which descend from the interval VW. Essentially, this is going to be independent of the ZTU for U smaller than V as soon as you condition on ZTV, right? It doesn't depend on what happened precisely between 0 and V. It only depends on what happened on the total size population for ZTV, okay? So there's kind of a Markov property in the V direction here. Okay. So, so now the question is, okay, so this is the analog of what we had for the purely branching process, no competition. So we in both cases we have this Dawson-Lee stochastic differential equation representation, right? So the question is there a way of, again, having a representation for this kind of process as the local time of a process H or a forest of trees? Maybe by pruning them. Okay. So let me go back to this idea that H encodes a real tree or a forest. So this is exactly what Christina was explaining at the on Monday about the fact that you imagine that you put some glue underneath, and then if you're Christina, you make a beautiful animation, and then you see that it gives you a tree. So I'm not doing that, so I did a very bad JPEG, a picture. But what you see here in red is kind of the beginning of the skeleton, or simplified schematic version of the skeleton of the tree, which is encoded by by this process H. And I can think of this as a tree or as a forest, it doesn't matter. The point is that if you have several trees, you can just join them at the root and you get one tree. So what I would like to emphasize here is that this particular set of trees here, of red trees, is endowed with two very useful structures. So one, I can put a Lebesgue measure on the skeleton of this tree. Okay? So that's not too complicated. And the other thing is that indeed there is an embedding of the tree. It's a planar tree, meaning that if I take 2 points on the skeleton of the tree, I can decide if one is left of the other or not. Okay. So this is completely clear if they are at the same height. But even if they are not at the same height, I can just look at which one is the highest. Then I take the ancestor of this one at the height of the second, and then I look which one is left of the other. And I have a notion of being left of someone in this tree, right? Okay. Yeah. And because I have this notion of being left of someone, I can easily define the notion of how many people do I see to my left. Okay? And what I mean by that is that, okay, so suppose I take one individual sigma in the tree, which is this black dot here. And unless this guy is a local infimum, and in those trees, the local infimum can be quite bad, but let's avoid this for the sake of this talk. This corresponds to one excursion above the level of this, exactly one excursion above the level of this black dot. And I can define the local time in the tree to the left of this black dot to be just the local time to the left of the beginning of the corresponding excursion of the process H, right? That's one way of making sense of the notion of local time in this tree. Okay, is this clear? So what I'm going to write as L sigma of T, of script T, is going just to be the amount of individuals in my red tree I see in this gray strip on this picture. Okay? So, okay. Right. So now what I would want to do is I would want to introduce a notion of pruning on the tree. And for this I'm going to use a result which is due to Abraham and Delmas, which is the following, which is, you can translate it as follows actually, is that if you take a Poisson point process of intensity theta times the Lebesgue measure on the skeleton of the tree, okay, so you are raining down points at rate theta on this red skeleton, and you are cutting everything which happened to be above marks of this Poisson point process, what you're left with is something which I'm going to call the P for pruning operation of the tree T and of this Poisson point process pi theta, okay, which is a connected component of the root once you've cut at those atoms. And this guy still has the law of one of those Levy trees, okay, but with a different branching mechanism. The new branching mechanism psi theta is just the old one plus theta lambda. Okay. So if you think about it now, and you're asking, and what you're doing is, I'm going to look at what can I say about the local time left of TV at height t of this pruned tree with rate theta. Well, it has to solve this by the theorem of Dawson Lee, it's going to solve the same kind of SDE, in distribution at least, as I had before, except that because now psi of t of the lambda is psi of lambda plus theta lambda, I should write here minus alpha plus theta. Right? If you remember the form of psi, this is all it does is it changes this alpha parameter, which is the death rate, from alpha to alpha plus theta, and instead of writing alpha plus theta here, I'm going to write the expression like that, which is equivalent, of course. Right? And you see that you're starting to get an equation which looks a bit like what you would want, right? Which is this guy. Okay. So if your function g that you're trying to get is just g of z is theta times z, then you're done. But you don't want g of z equal theta times z, you want g of z equal z squared, let's say. So if you want g of z equal z squared, it's a bit more complicated what you need to do. Because, okay, so if you want g of z equal theta times z, of course, the small g function is just a constant equal to theta, right? And that means that you are raining down points, you are killing at a rate which is completely uniform, whatever the size of the population you see to your left. But now you want to rain down point on this red skeleton at a rate which depends on the local time you see to your left, right? So the way I'm going to do that is I'm going to introduce a new Poisson point process, but this time I'm going to have a mark ui. So this one is two-dimensional. Sigma I is a point on the skeleton, and ui is a point on R+. Okay? And the intensity measure is again the Lebesgue measure on the skeleton times Lebesgue measure on R+. Okay? And okay, so then let me explain how you prune with this kind of process. So let me take phi, which is a function from the skeleton of t, or the tree t if you want, into R+. And you can think of it as deterministic for now if you want. And let me call pi phi to be the sigma I in my Poisson point process sigma I ui, such that ui is less than phi of sigma I. Okay? So if I do that, you can think of this as I'm pruning such that at position sigma, I'm pruning with a rate which is phi of sigma. Okay? That's what I'm doing by doing this. And okay, so if for instance I'm pruning my tree t with phi which is constant equal to theta, this is exactly pruning with rate theta as I explained before. This is the same thing, of course. Okay. Okay. So now I want to take phi which is not actually deterministic, but which is going to be random, and which is going to depend on what it sees to its left. So I'm going to say that phi from t to R+ is adapted, is an adapted intensity if phi of sigma is measurable with respect to what it sees in this blue rectangle here. And in this blue rectangle, I put the whole process H in the blue rectangle, so everything concerning the branching in the blue rectangle, but also all the atoms which fall in the red part, on the red skeleton, which is in the blue part. Okay? So, okay. And in that case, I'm saying that this guy is not adapted at intensity, right? Is this clear? Okay. So, our theorem is the following. Our main result, if you want, here in this part, is the following, is that almost surely, so almost surely here refer to the Poisson point to the process H and to the Poisson point process pi sigma I of sigma i's and ui's. You're going to have a unique phi star, which is going to be an adapted intensity, such that phi star of sigma is actually going to be equal to small g of the local time left of sigma in the prune tree by phi star. Okay, so of course this is a fixed point equation, right? This is an equation. You have phi star on both sides, so it's not even clear that you have the solution. But we say that there is one, and there is actually only one. And what it says is that it's possible to prune your tree in such a way that the rate at which you prune here is exactly the local time of the tree that you see to your left once you have already pruned. Okay? So that's why this is a bit delicate. And the second thing we say is that this guy is actually a good candidate. So the tree which is pruned by 5 star is in fact a good candidate to be what you want to find the solution of your SDE with this negative drift minus capital G. Okay? And indeed, if you take the local time of the pruned tree by 5 star, what you get has the same distribution as the solution of this SDE. Okay? And this is for T in T and V. So let me try to explain very briefly why this should be true. Okay? And I think that the idea why this should be true is quite nice. So, so the proof for the first part, that is that there exists 5 star, actually fits on one slide. If you are willing to believe me on a few things. So essentially, so what you want is you want to prove that there is a solution to a fixed point equation, right? And for these kind of things, what you do is always the same. You do a Picard iteration, and here the Picard iteration is the following. So you start with phi 0, which is the rate at which you prune, right? Remember that phi is the rate at which you prune at position sigma. So phi 0 is 0, so you don't prune. Okay? So if you don't prune, well, the tree pruned by nothing is the whole tree, right? So then, once I have phi 0, I need to define phi n plus 1, given that I have phi n already. So phi n plus 1 is just g. Okay, so phi n plus 1 of sigma, position sigma, well, it's going to be g of the local time left of sigma in the tree pruned by the previous guy, by phi n. Okay? So I have phi n, I prune. This gives me a tree which I call Tn. Okay? I take the local time of this tree left of sigma. I take g of that, and that's my new phi n plus 1. Okay? So if you do that, and you think, okay, what is phi 1? Well, phi 1 is just the local time of the whole tree. So phi 1 is big. In fact, it's going to be bigger than anything you can get, because as soon as you prune your tree, you're going to get something smaller, right? G is, capital G is increasing. Yeah, it's a capital G, not a small g here, sorry. So, okay, so you get T1, and T1 is a subtree of T, right? It's smaller. So then you ask, what is phi 2? Well, phi 2 is the local time of T1, which was smaller than T. So that means that phi 2, well, phi 2 has to be, so it's bigger than phi 0, which is 0, but it's also smaller than phi 1. And you go on like that. So what is phi 3? So phi 3 is the local time of T2, which is, of course, smaller than it's a subtree of the whole tree, but it's bigger than T1 because now you're pruning with a rate which is less, and so on. And what you get is you get a sequence of intensities which are like this, right? So they are doubly converging. So the terms which are odd are decreasing, phi 1, phi 3, phi 5, and the even terms are increasing. Okay? And what we are able to prove actually is that in fact there is a unique limit to both sequences. Okay? And how do you do this? Well, also as usual with a Grunwald type lemma. All right, so that proves, and of course, once you have this phi star here, this phi star is a fixed point of the equation by which I define phi n plus 1, which is exactly the equation I wanted to solve here, right? So I have a solution. I have proved the existence and unicity of the solution to this equation like that. Okay, so how do you prove now that this is a solution to the right SDE? So the way we do it now, so I should say this is a work in progress with Joaquin Fontbonard and Maria Clara Fittipaldi. In progress soon, finished, hopefully. Is you do a discretization. So you fix epsilon positive and delta positive, and what you're going to do is we are going to build a process which is going to be pruned in a discretized way as follows. So first, I stop my process at t delta, so I wait until I have delta units of local time at 0, and then I start a CSBP with no killing, with killing at rate 0. And then I erase everything above epsilon because I just want to construct it until time epsilon. Okay? So the local time of this thing between 0 and tv with v less than delta and t between 0 and epsilon is just a CSBP started from v, which lives for time epsilon. Okay? So the next thing I do is I will take care of what happened between t delta and t2 delta. So in this interval of local time, I do a CSBP with constant killing at rate delta. And that I know how to do because I can use Abraham and Delmas results, right? So this is just the H process of a tree which is killed, which is pruned with a constant rate delta. And between T2 delta and T3 delta, I do the same, but now I prune with rate 2 delta, okay? And so on. And if I continue, then I need to do the same thing between time epsilon and time 2 epsilon, so the second strip. So I start on the left. On the left, I continue my CSBP with rate, with killing rate theta equals 0. Then between T epsilon delta and T epsilon 2 delta, because now I look at, it's as if I was starting again completely from scratch at time epsilon. So I wait until I accumulate delta unit of local time at level epsilon and 2 delta unit of local time at level epsilon. And in each, what I'm doing here is that in each rectangle of the form k delta, k plus 1 delta, and I epsilon, I plus 1 epsilon, I'm killing at a constant rate. And the rate is essentially the local time I see to my left on the lower left corner of my rectangle, that is k delta. Okay? So in this kind of rectangles, I kill at rate k delta. And doing this, okay, I can build my whole process. And then the work here is to prove that when you let epsilon and delta go to 0, well, on the one hand, you get something which converges to the solution of the SDE. And on the other hand, you get exactly the tree with the pruning phi star. Okay? But I hope that you believe me that this works. All right, so I have 20 minutes, so I can go to the second part of the talk. So the second part of the talk, I'm really happy to talk about it here because this is something actually that started more or less when we were visiting here a few years ago with Leonid Litnik with his ear and Lorenzo Zambotti. And is based on a joint paper also with Leif Doring. So this is about exceptional times for stable Fleming-Veaux with mutations. So the good news is that it's if you haven't followed what came before, now you can start again. Because it's a new question, but you're going to see also that after a while, it's going to come down to really the same kind of question and techniques. Well, I hope to convince you of that at least. So, okay, so let me just introduce again very quickly what is the classical Fleming-Veaux process that Alison mentioned this morning. So, this one is also the model for the evolution of a population, but this time of fixed size. Okay, so the size of population is going to be fixed. So I'm going to think of it as scaling limit of discrete models. So you can think of this as so you can take a Moran model where you have successive discrete generation of fixed size capital N, and in this model, each individual has new I offspring in the next generation, and what's very important is that the new I are exchangeable. So, okay. So if you do some mild assumption on your new I, so that they have a second moment, say, what you're going to get, okay. And the other thing you're going to do here is you're going to give a type to each individual. So this was a small a, capital A this morning. So for me, the types here, I'm going to represent them with colors, and you pass your type to your descendant, okay? And then you're looking at the measure which represent the type distribution, okay, in your population. So imagine that each color is coded by a point between 0 and 1. Okay, so uniform variable, IID variable between 0 and 1. Those are the types, the initial types in the population. And then I look forward in time how the empirical measure of the type is evolving, right? So the scaling limit of this process is a Markov process on the probabilities on the interval 0, 1, and this is called the Fleming-Vio process, right? So what's interesting is that, of course, because I started with types which were IID uniform on 0, 1, it means that my initial measure, mu0, is just a uniform measure on 0, 1, right? But for any strictly positive time, ut is immediately just a finite sum of atomic masses, right? So the number of types, this is the same phenomenon as the fact that coalescence come down from infinity. In fact, this is related, as we know, to Kingman coalescence coming down from infinity. Right, so that's just the classical Fleming-Vio. But what I want to do is I want to add mutations to this, okay? So what you can say is that, okay, in each generation, in addition to the mechanism I explained, you add the possibility for each individual to suddenly carry a new color that you have not seen before. Okay, like this guy here is a mutant. So he's green, like Hulk. And then you can, and you do this in a way, so I think that, so I'm not sure about the exact probability for which I hope my scaling is right. So I think it's theta over n, the probability for a mutant for each individual has a probability theta over n in each generation to be a mutant. Then you're going to get something non-trivial in the limit. Or is it n squared?
Well, probability of having the same ancestor in generation before.
Yeah.
So it's 1 over n in the bright fish model, but it's not in any Chinese model.
Okay.
But you just have to scale things
Yeah,
right
exactly.
so that
Okay.
the
So it's
probability of
theta.
difference is the same as
Okay.
probability of mutation.
Yeah. So it's theta of some function of n. Sorry. So that the scaling limit is right. And if you do that, okay, so you get now an interesting scaling limit for the measure valued process, because of course you start with this uniform distribution, and then because of the Fleming-Vio evolution, it wants to go down to a finite number of atomic masses immediately, but you have those mutations that keep appearing continuously now, and that are keeping the number of types up. And so the question, in fact, is, so if you look at any fixed time t, almost surely the number of types is still infinite. Okay? But the question is, do you have exceptional time at which the number of types is still finite? And the answer is given by Schmulen, and it says that the probability is either that those exceptional times exist is either 0 or 1, and it depends on theta. There's a transition. So let me see. So this is okay. So if theta is not large enough, you will see no such time, almost surely. But if theta is larger or equal to 1, then with probability 1, there exists those exceptional times exist at which the number of types is finite. Okay. And the proof that was given originally by Schmulen is very analytical. So one of the side products of this, what I'm going to present now, is that we're giving a very probabilistic proof of this, which is going to come next. Okay. Right. So now I want to go to generalized Fleming-Vio with mutation. Okay. So what I do is so this is a set. You can also think of them as a scaling limit of Moran models, but now the reproduction law is such that it has a much higher variance. In fact, you can think of them as being in the. So one way to obtain it, is to do the following. So each individual has a reproduction variable xi, which has a tail which is in y minus alpha. And then what you do is, because you want to keep your population constant, you just sample capital N individuals of this whole offsprings which has been produced. And if you do that, hopefully the scaling limit, so again my scalings are, I think not right, but you get what's called the generalized Fleming-Vio process with alpha stable branching mechanism. Okay? And again, you add those mutation at rate which is theta with some other function of n, which is n to some power depending on alpha here. And you get this ut, okay, which is going to be the scaling limit. And it's going to be generalized Fleming-Vio process with mutation at rate theta. And what we proved is that it doesn't matter what theta is, there is no exceptional type. Okay? At all times, the number of types is infinite. As soon as alpha, so I didn't say what how alpha is, so alpha is between 1 and 2. Alpha equal 2 corresponds to the Kingman case, to the usual Fleming-Vio case. And as soon as alpha is strictly less than 2, well, you have no exceptional times, whatever theta is. Okay, so how do you prove this, and what is the connection with the first part of my talk? Okay, so, right. So if you think about the usual Fleming-Vio process, okay, there is a well-known connection with the Feller diffusion, with the quadratic branching process. So if I take Zt to be again the flow of CSVP with V between 0 and 1, the flow of CSVPs with quadratic branching mechanism, so you can think of them as being the local times of reflected Brownian motion until I accumulate 1 unit of local time at level 0. So if I take this Zt and I renormalize it by its total mass, okay, so I can think, the first thing is Zt of V, I can think of it as, because for each t, this is an increasing function of V, I can think of it as a distribution function of some measure. Okay? So I can really think of Zt as a measure valued process. So now I take this measure valued process Zt and I renormalize it by its total mass, which is just Zt of 1, right? Zt of 0. So I call this mu t. And now I time change mu by this, the inverse of this function st here. And this is now a Fleming-Vio process. Okay? So if I want to do the same with mutation, well, it's not too hard. So what I do is I take my process, my reflected Brownian motion, until I accumulate 1 unit of local time at level 0. And in addition to that, I give myself a Poisson point process of Brownian excursion. Okay? So here, EI, SI, and UI is a Poisson point process where EI are Brownian excursions, SIs are the time at which I start my excursion. This is the level at which I put the excursion on the left. And UI is the color, it's the type. It's a genetic type of excursion, okay? And the measure intensity of this Poisson point process is N of dE, which is the Ito excursion measure, time ds, time du on 0, 1, okay? And now I take the local time of this new thing, including the colored excursion on the left, okay? And this gives me, again, a Zt, and I do exactly the same. So I renormalize it, and so Zt of V is this LTV T, which is the local time of the white stuff, which I had before, plus the local time at level T of all the excursion, such that their UI, their color, is less than V, okay? And if you do that, well, this is again, of course, an increasing process of V, so I can again interpret this as a measure value process, and renormalized I get mu t, I time change by the same thing, and what I get now is the Fleming-Vio process with mutation at rate theta. Okay? So just note that what's interesting here is that if you think about what is, let me think of Zt as the total mass. So this is Zt of 1, or Zt of V, in fact, if you want. This is going to solve the following stochastic differential equation. So you're going to get the Feller diffusion noise, which is here, plus a positive drift theta dt. Okay? And this is, of course, what you get here is the equation for a Bessel, right, of dimension theta over 2, 2 times theta, sorry. And what I've just explained here is a Piedman-Yor decomposition for such processes. And what you know, of course, is that theta equal 1 here is going to be critical for whether or not such a process can come back to 0, right? Because this corresponds to the question of whether or not you're looking at the modulus of a Brownian motion in dimension 2. Right. So theta equal 1 corresponds to dimension 2. Okay. So I want to do that I want to do the same now, but for generalized Fleming view process with mutation at rate theta. So, okay, so first of all, I need to define a bit better what I mean here. And the way to do that is again to go to the dose-only stochastic differential equation. So here, what I write on the top, so this is a slightly simpler expression as before because I don't have a Brownian noise. Okay, the Brownian white noise is not there because I'm only considering the alpha stable case. So the first thing here is a continuous branching process with immigration. Okay, and so you see that this green term on the upper right is what was the negative competition drift earlier. So now it's a positive term. And you also see that it's simpler in the sense that it only depends on GS, on G of ZS of 1, okay, on the total mass. That's because the arrival of mutation should be somehow proportional to the total population. And this is studied, for instance, by Ganguly in his book, and he calls this continuous branching process with interactive immigration because the rate of immigration depends on the total mass. And the second equation here, which is also in dose only, is the equation for the evolution of the Fleming view with mutation rate theta. Okay. Right. And here in this equation, m is a Poisson measure. It's not compensated, and the intensity is given by ds d nu r minus 2 lambda of dr, where lambda is beta 2 minus alpha distribution. Right. And so the solution of this SDE is what I call the alpha stable Fleming view with mutation rate theta. And you can again do try to do the renormalization and time change. And what you see is that, so you can do a proof for this, that if you take your continuous branching process with immigration Z, you renormalize it by its total mass and time change it like that, then what you get is the alpha stable Fleming view process with mutation theta. So the question is, do you have a Pitman-Yor representation for Z? So what you want to do here is you want, I'm going to try to explain this, yeah. Okay, so what I'm doing here is you see the function, the immigration mechanism I'm putting here is that I'm trying to immigrate at a rate which is the total mass, Zs of 1 to the power 2 minus alpha. So why is that? Well, it's because my time change, you see, is going to eat a power 1 minus alpha of it, okay? And the renormalization is going to eat another power 1. And that's going to give me mutation at constant rate theta in the Fleming view, okay? Because 2 minus alpha minus 1 minus alpha minus 1 is going to be 0. So what I want here is I want to throw my excursions here on the left at a rate which is proportional to the total local time to the power total till 2 minus alpha, sorry. So again, you're having one of those fixed point equations where what you want is you want to define a process Zt of v, which is the local time of the white stuff plus the local time of the excursion. So now my Poisson point process has an extra dimension, AI, which is I'm going to use for filtering, okay, which is a mark on R plus. And I only keep the excursion such that AI is less than capital G, where capital G here is just a constant times this to the power 2 minus alpha. So I only keep the AI which are less like that than this, and therefore I'm throwing at a rate which is proportional to G of ZSI of 1, right? And again, this is a fixed point equation, so you have to show that there is a unique solution to this equation, and again we do this essentially by Picard iteration. Okay. So let me go back to the and wrap up with the initial question I asked in the second part, which is, can you find those exceptional times? Okay. So So now I have, so what I'm saying is that because my Fleming view is a time change, essentially, of the renormalized branching process with immigration, if I have exceptional time for the Fleming view, it can only happen if I have exceptional height for this CBI process, continuous branching with immigration, at which I see only a finite number of types. So what is a finite number of types here? It's a finite number of excursions which are crossing a level. Okay, so I'm looking for a green line such that it crosses only finitely many excursions. So of course, you see the problem cannot come from the white part, because I know that for any positive height, I only encounter finitely many excursions. Okay? So the only thing I have to worry about are the colored excursions on the left, the one which have immigrated. That sounds bad. So the only thing that counts for this, of course, is when do these excursions arrive and what are their height. Okay? So let me represent what I tried to draw here is that for each of the small excursions on the right, I just put a small stick which is planted at the height where the excursion starts, and the length of the stick is just the height of the excursion. Okay? So the question I'm asking is, can I find a point now which is not covered by the shadow of the sticks? So what I mean by that is that you imagine that each of the sticks has a shadow at a 45-degree angle, and you're looking at the point of the real line here on the y-axis, which are covered by only finitely many shadows. Okay, and in fact, if you have a point which is covered by finitely many shadows, you see it means that to uncover it, to make it see the sunlight, you only have to erase finitely many sticks. And of course, this is something that you can do with a finite probabilistic cost. Okay, and that means that if you have points which are covered by finitely many shadows, you must have points which are completely uncovered. So the question becomes, you give yourself a Poisson point process. Those are the small cross on the left here with a certain intensity on R plus cross product R plus, and you ask whether or not the real line is going to be uncovered by this. And this is a well-known problem for which you have a criterion which is called Shep's criterion. And in fact, you just apply this criterion and you see that for alpha stable process, as soon as alpha is less than 2, then the criteria tell you that no point is left uncovered. And in the case where alpha is equal to 2, then you see the transition at theta equal 1 for the existence of uncovered or covered point. And I'm going to stop here.
Very much, yeah. Any questions?
Yes, so considering the first part of your talk, I remember also vaguely work by Pardot.
I didn't mention that. I should have mentioned it. Thank you for reminding me of doing it. So this is very related to a very beautiful work of Pardot and Wackelbinger. But if I understand correctly, what they do is, so they want also to define the genealogy of those processes with competition. And what they do is they take a reflected Brownian they define a stochastic process which is essentially a Brownian motion with a negative drift, which is the local time to the left that is right. But because you have to be able to define the solution of this SDE, that means that you are only able to handle quadratic branching mechanism. Because of course, if you want a more general branching mechanism, then you don't have an SDE. It's not anymore a Markov process, so it cannot be the solution of an SDE, right? But this notion of course, this was done independently, but the notion of being killed by the individual on the left is completely related to what Pardot and Wackelbinger called the trees under attack from the left. Yes. Yeah.
In the case that you have exceptional times, can one say something about the Hausdorff dimension of the set?
We haven't said anything. Probably yes. Yes. I think this is yes. But no, I don't want to say anything stupid now. Essentially, once you have once you have the measure of your point, now it's become a very simple question, right? You have just an intensity on R plus. You take a Poisson point process on R plus cross R plus, and you want to say things about this. So this is something that, for instance, Victor Rivero here has studied about the set which is less than covered, which is a regenerative set, is it called? Yes. And typically studying the order of dimension is a question which is, I think, well done.
Fitzsimmons.
Yeah,
Fitzsimmons.
I wanted to make the same remark as Jean, and just one more comment that they have this local time drift in their paper, Pardue and Weitelbinger, and this is, suppose, in their case, more or less equivalent to your pruning of trees.
Sure. Yeah.
And, but this approach is related also to an old paper of James Norris, what considered this Boolean motion with local time drift.
I didn't know that. Okay, thank you.
Any more questions? Okay, thank Julien very much again.